I'm going to talk about the sun from elementary physics point of view. Doesn't mean to say that Newton and Maxwell is as far as I'm going to go with the physics. Of course, in solar physics, we end up dealing with people like Schrödinger. We get into the 20th century as well, and even Zeeman and all kinds of interesting people. But anyway, I want to draw your attention to one thing. Wigner's dictum: the important problems in physics are rarely solved, they're either forgotten or declared to be uninteresting. So I'm going to point out that while we're used to looking at the sun, it does some very strange things from an elementary physics point of view, and I want to see if we can interest people in perhaps getting into solar physics and out of astrophysics, which is hopeless, I know, but it's worth a shot. The sun is as boring as it looks. That's what it does, okay, unless you start looking at different wavelengths, etc. I'm going to give you a one-page solar biography. I was born 5 billion years ago from overweight, exploded parents. I clumped into a fast-spinning spheroid with an umbilical disc that shriveled into 8 or 9 small children, and the doctors on the child number 3 can't quite decide which one it is. Right now it could be 8, 9, 10, 11, 12, I don't know what it could be. But one important thing is I can't actually abide electric fields because of the free charges. I'm in a plasma state. The doctors say I'm in a plasma state anyway. I was born with the magnetic fields that slowed the spinning to a sedate 1 turn per month, for which I burp up periodically to give me irritating spots. And the spots appear every 11 years or so, but sometimes quieten down for a century or so. We seem to accept this as being okay. You know, we have no clue as to why that would be. The doctors worry about my spots. In 1859, a spot burst and really got their attention, and I'm going to get into this a little bit later. The doctors say I'll keep having spots as long as the pesky magnetic fields don't start at monopoles, and providing I keep on spinning. But then, what do the doctors know? In America, if I put this up, a lot of people don't know what I'm talking about. Seeing is believing. So this is before I get somewhere. This is a picture of something going on at relatively low resolution from a distance. When we look at the sun, we're looking at things that we can't really see. It started again at a higher resolution. What this is an example of complexity. Even the JPEG or whatever it is compressing thing gets confused. It thinks there's a solid object there. Machine recognition thinks it's looking at something solid. We think we're looking at something solid. Whenever we look at something from a distance, we have to be very careful what we interpret. So what we're seeing here is very complex, ordered behavior. In mathematics, you have a thing called complexity theory, and that is that the sum is much bigger than the individual parts added together. The non-linearity is inherent in any system, like an immune system, like a flock of starlings. Does anybody know the collective word for that? I didn't know that either. It's called a murmuration. I feel like I'm going to collapse with a heart attack right now if I say that word. I think this is a remarkable thing. Namely, that what we better remember when we're looking at something like the sun, we might be seeing something like that. The individual atoms, of course, the atoms have to obey Newton's laws, essentially, and some quantum mechanics. The birds can do what they want because they can fly around in a fluid. But nevertheless, they exhibit collective behavior much bigger than the sum of its parts. Okay. Sobering reminder from the 19th century. This is the philosophical part. I hope there aren't any philosophers in the audience because I'm not, but I'm going to quote this one. There's a guy in the date's important, 1835. Course on positive philosophy. It doesn't mean positive thinking. It's a particular way of dealing, a group class of philosophy. Basically, he's saying you regard any notion concerning the true meaning of temperature of the various stars are forever denied to us. 1835. 1859, Fraunhofer, Kirchhoff and Bunsen show up, and they find a lot of spectral lines that are in absorption in the sun's light, but which show up bright in the lab. This was the beginning of real astrophysics. I'm not talking about astrodynamics, which began with Newton, with the observations of Copernicus, of Tycho Brahe. I almost said Tycho Brahe. I've been in Colorado too long. Anyway, here's an example. An example where you can show that the brightness temperature of the sun is derivable directly from observations, and that has physical meaning. We can't go anywhere near the sun with the thermometer, but here it is. Okay, we all know what we're talking about. So very basic things. A lesson from Kant's philosophies is, I think, that, and what I want to give to the young people is that what seems impossible now may really come alive in decades to come. You know, we've seen what happened with the gravitational wave thing recently. I don't know what the implications of that are, but I'm very excited for young people now because we really don't know what's around the corner, ever. We think we do, and you think we might be in a mature area, and in my abstract I put even senile area of research, but you never really know, and there's a new class of telescope coming online. Okay, let's get into some physics. What about Newton and Maxwell? Newton plus Maxwell equals alpha. That's a genuine equation. I can prove it. I can take a theorem and do all this stuff, but I'll do it right now. Let's get there. What does a non-magnetic sun looks like? It looks like a sun that someone like John Latanzio might model, for instance. He wouldn't bother with anything so boring as small as this, but nevertheless, what it has is it has core burning in the interior. It's evolved onto the main sequence. It has a radiative core. It has a convection zone envelope. It has a photosphere where photons get out. And more than anything else, it has basically timescales of about 100,000 years. That's if you switched off some energy inside the convection zone for a while, it would take that long for it to sort of dissipate away. So remember that number, 10 to the 5 years. It also has, because it's an elastic ball, it also has oscillations, and apparently they want to appear about 5 minutes. So that's, you know, rather more often than the buses come through Monash University if you want to go to Clayton or something. Okay. That's in the fiction section of the library. There is no star that we know about that ever will look like that. And that's an interesting...
Perfectly consistent with my model.
Perfectly, perfectly. So where is the M in the MHD? Magnetohydrodynamics. That was a hydrodynamic model. Well, this actually started in the 19th century, really a long time before even the discovery of the Zeeman effect. Here is from Young's book, 1869, I believe. That's the 1892 edition. But you can see spectral lines, a sunspot. So here's a spectrum. Here are the spectral lines and various things. And these things are split. And they didn't know why that was. They just thought the lines were split by, I don't know, whatever, some physical mechanism they didn't understand. Here is a physical detection. If they'd known that there was magnetism there, that would have been 10 years before Zeeman discovered the Zeeman effect. Okay? So we know that there's stuff. And if we go to the sun, modern observations, let's focus on the left-hand side. What you can't see here very well is that it looks like a bar magnet. The north and the south have these bar magnet-like structures. The stuff coming out at the sides, these would also have bar magnet-like structures if it weren't for one thing. And that's that the sun has a solar wind. And for some reason that we don't understand yet, the solar wind exists and it pushes aside and drags with it the magnetic fields. We sit inside the solar wind somewhere on the east-west line, and those solar wind particles pull out the field lines that would have looked like that. They get stretched out further, and they get stretched out further until it becomes at the very point of contact a current sheet, and we're living in that environment. So we have a poloidal component going north-south, and that there is another, and this was seen from eclipses in the 1900s, but in the 20th century, beginning with Hale, shortly after the Zeeman effect, in 1896, he discovered the Zeeman effect in the sunspots. What's different about these two things is that the poloidal field on the large scale seen in eclipses is like a dipolar potential field, like a bar magnet. The sunspots, however, have a component which is mostly east-west. So this is more of a toroidal component, a torus. And our current understanding of the solar dynamo, why it will want to do weird things like change every 11 years, well, let me first tell you the fact. In 1920, Hale discovered the remarkable thing that the whole polarity of the sun changed sign in 11 years. And then it reverted back to the original sign 11 years later. That's astonishing. This sun is not a small thing. It takes the Earth how many thousands of years to do that? I can't remember. Of course, the Earth has a magma core. It's much more viscous. Things that happen a bit slower. So something is making this object change its magnetic field on timescales of 11 years, when the shortest dynamical timescale I know about that's reasonable is the outside of magnetism, Kelvin-Helmholtz, is hundreds of thousands of years. So we have two components of the magnetic field, toroidal and poloidal. And if we're going to make it change sign every 11 years, the toroidal component, turns out the toroidal component does the same thing. Changes sign, and let's get into that. And the whole idea of a dynamo is to go from poloidal into toroidal, complete the cycle back into poloidal of opposite sign again. That's the idea behind solar dynamos currently. What is a dynamo? A dynamo is simply something that is able to take some kind of ordered motion, some kind of ordered energy, and in this case it's going to be kinetic energy of fluid motion in a charged plasma, and sustain a magnetic field against the dissipation that's inherently present due to collisions between electrons, protons, etc., etc. Okay? So here's the magnetic sun. This is, what do we have inside here? We have convection. I'll get into another thing at the moment. It also has differential rotation. The differential rotation is not random. It's very ordered, as we'll see in a minute. The convection is chaotic, almost by definition. And so we have two things there. We have a chaos and we have differential rotation. The magnetic sun has things like a corona around it and a solar wind. And this is in the non-fiction part of the library. Okay? Now, a major question is, okay, given that we see these large-scale fields, not only why is they changing on 11-year timescales, how can this be? And we'll get to magnetohydrodynamics in a moment. But why does the magnetic field appear in spots? Remember when that first thing I showed you, the magnetic field wasn't diffused over the surface in some way. It was highly concentrated into a spot. From first principles, we don't have an explanation why that would be. We've got used to seeing sunspots since, they started blinding themselves after the invention of the telescope. And before that, with ancient Chinese measures and stuff like this, we've got so used to thinking of sunspots that we stopped thinking about what the hell they actually are anymore. We have no explanation as to why that would be. And I'll give you an example. Here is a beautiful model. We can model them beautifully. Clever people can model them beautifully. And here's an example where you have a visible generated image. At the bottom you've got the vertical slice underneath it through the middle of this thing, and that's showing you magnetic field, I believe, strength. No? I don't know what that's showing, but it's something really. It's not velocity. It's maybe something to do with the magnetic field anyway. But it doesn't actually matter for this thing. But you say to yourself, we've solved it. We put it in a box. We've solved it. The problem is, it's not possible to make anything look like that unless we do some funny business with the boundary conditions. Funny business with boundary conditions to a physicist is a no-no. It's a good thing in a way because it means you're missing the physics. The solutions you get depend so much on the boundaries. What Matthias Rempel has to do here, he has to squash the top of the atmosphere in order to make something look like a sunspot. So irrespective of how, and what he's done at the bottom is to gather up stuff from underneath, not artificially, but artificially, but guided by numerical dynamical simulations of flux coming from beneath. And he's tied it into a bunch, and then he's let it go. And he can only find something that looks like a sunspot, not only if he pinches it together like this, but also he squashes the stuff from above. So apparently the atmosphere above the sun is important in forming something like a penumbra of a sunspot, which is a very interesting thing. So from first principles, we don't understand that. This is what the differential rotation looks like. The contours show you, differential rotation. Just like in the weather maps and things like this, so they're constant velocity. So this is the velocity as a function of radius and latitude, and it's axisymmetric. And this was done through the sounding of the 5-minute waves in the late 1980s. And so what we have here, and the zone is in hatched, is the zone that's inaccessible to the inversion. Okay, So what we have here, before this we had no real idea. Well, we had some ideas based upon theory, in which these things would have been more vertical, solid rotation in cylinders. But it turns out to look like this, and there are two regions there you can see where you have very steep shear. So if I go radially out from here, we'll have a very steep increase in the gradient, increase in the differential rotation. And furthermore, if I go in this direction, I have a steep increase in, a less steep, but a rather significant increase in differential rotation. This is called radial shear. This is called latitudinal shear. And shear is one of those things that generates magnetic field. It's like pulling on chewing gum. Okay, so this was a big surprise, and I regard this as the last really big discovery in solar physics. Many of you will have thought that the neutrino physics issue was important, and indeed it was, but it was much more important for particle physics than it was for solar physics. Okay. What is magnetohydrodynamics? Einstein changed Newton's formulation to fit Maxwell's equations. That's what he did. He noticed that the Galilean transformations just made nonsense of Maxwell's equations. MHD can be thought of the reverse applied to a conductive fluid. So instead of going a whole hog with the relativistic formulas, and what you do is you keep your transformations of the fluid quantities and to order V over C, but you maintain the Galilean framework, and you work with Maxwell's equations to order V over C. And the amazing thing is that Einstein didn't get a Nobel Prize for that work, but then Alfvén got a Nobel Prize for his work in sort of undoing it in that sense and making it a tractable and simpler theory. The really ironic thing about it is that Alfvén came not to believe his own theory before he died, which I think is more a reflection of his own psychology than it is of what physicists think today. It is the simplest theory of a magnetized plasma, and it applies in places where you believe you have, in the usual hydrodynamic assumptions, many particles in a phase space element, etc., etc. So, how do we make MHD? We take Maxwell's equations, we set the velocity of light to infinity, that's the dd by dt term, so that everything, we assume, in other words, the physical system is not that big. Newtonian momentum equations, and we adopt order V over C relativistic transformations, and those are given here. And if you expand these out in a classic plasma textbook, you'll find yourself J is sigma E primed in the frame. So in the frame of a moving fluid element, I put a prime. In the frame of the laboratory, I don't put a prime. And so here you say, the first one there, J prime is approximately sigma E prime. That's Ohm's law, okay? But you notice you've got an E plus U cross B there, because of the transformations. If we combine those equations, we end up with an equation called the induction equation, dB by dt. If we understood this term, the solar physics would be finished. We would be ended, right? So all we don't understand about solar physics in the context of MHD is contained in this equation here, coupled with the equations of motion, because this is not separate from the equation of motion. This is a nonlinear term, u and b, velocity and b, they depend on each other. These are things we would have to solve for if we were to build a computer program to try and solve for it. And u and b appear in two different equations. One is the induction equation, one is the equation of motion. That's MHD. So here we have potentially, if we have a changing magnetic field, say at the pole of the sun, we want to come up with a prescription in which we have sources and sinks, perhaps on the right-hand side, the first term, and the term on the right side is always a sink, and this is due simply to the J equals sigma E. This is just ohmic dissipation at this point. Okay. Let's look at the sun, and that second line down, we end up with certain parameters in SI. We notice that the magnetic Reynolds number for the scale of the sun is 10 to the 10. That's 8 orders of magnitude larger than any other number in the thing. That just measures the importance of the first term on the right-hand side compared with the second. And we notice the diffusion time. Diffusion time, what is that? That's if we ignore the first term on the right-hand side and just take dimensional analysis to get 1 over t equals eta b over L squared, where L is given there, 10 to the 9 years. So if we started with a sun with a magnetic field of 4 times 10 to the 9 years ago, it would have decreased by e to the minus 4.5. And yet the sun is changing sign in its magnetic field every 11 years. So clearly, we don't have a passive decaying sun just resistively diffusing away. The bottom line shows us the induction equation expanded out into a different form. Here I will ignore the diffusion term, because after all, if the ratio of the first term to the second term on the right hand side is 10 to the 10, that's a pretty good approximation, you'd think. So I'm going to keep the first term only, and then I get the bottom line. And the physical interpretation of those mathematical things are stretch, shear, and compress. And we saw already that there were big shear layers in the sun. I'm talking not here about generating tiny amounts of magnetic field in small areas on the sun. I'm talking about the global magnetic field. Sunspots appear in ordered patterns. They represent a large-scale toroid of flux. The eclipses show us the other component, which is a poloidal component. So what we're going to need to get order out of chaos here, in complexity theory, what we would need to get emergent behavior on large scales out of a bunch of little things that don't know about each other, namely the packets of fluid on very small scales, then we're going to need to break the symmetry in the sun's physics in some large-scale way. And it turns out that the shearing is the most important one of these things. I want to draw your attention to ideal MHD formally, where you go to this limit, where you ignore all dissipation whatsoever. This means it's like going to when you sit and you're having your teeth drilled out in the dentist, and the kids are left to play, and they have one of those toys where the beads go along the wires, those ones. The fluid is the same, the magnetofluid is the same. The beads have to go along the wires. If the field is very strong, it's just like what the kids are doing. They're moving the plasma along the wires. If the field is very weak, they can pull the beads around, and all the magnetic field has to move with it. And they can, furthermore, they can twist it all up if they want. If they twist it all up, and if I add up the amount of magnetic field per unit area, every time they twist it, magnetic field goes up. They're building a dynamo. Okay. Of course, they'd never allow that, because the kids would probably put it around their neck, and then that's just not going to happen. So, but the point is that the frozen field condition means that if those two contours at time t to t plus delta t comprise an area of all the same fluid particles, then that line on the right-hand side going out is not permitted. All the lines, you conserve the flux through each volume of element. So topologically, you can identify a flux tube, a tube of flux, entirely by a flux, by a volume of particles inside a certain volume in that. Once that's set forever. So that, okay, let's get to the consequences of that. This is an example. This is the kid playing with the thing, and they're twisting up the magnetic field lines, and it stopped to it. Then they start twisting again. And but the thing is, the topology here is the same. The topology in the sense that if I start from one place on the bottom, let's play that again. So those little tiny loops, see those loops? Those loops, even in this mess, still connect to the other one. And I think that you can see that there's been an injection of electromagnetic energy from beneath here, such that that state is a lot more energetic than the first one. That's because the field lines are much longer. You're doing work stretching the field lines. They're much more twisted. There's a lot of shear in this system. There's a hell of a lot of free energy in that system. And the sun somehow has to deal with situations like this, because after all, this could be the photosphere, and these could be the coronal field lines, and they're going up. But we never see anything anywhere near as complicated as this. Something else happens, even though the magnetic Reynolds number is very, very large. Okay? recommended, I want you, if you can pass that around. This is a small book, Conversations on Electromagnetic Fields in the Cosmos. It takes you from undergraduate and maybe master's level electrodynamics with all the nasty business of the boundary conditions and all this other stuff, safely into understanding how to deal with the astrophysics and the plasma physics in the simplest conceptual way you can imagine. It's my favorite book ever written in this area. Notice it looks like your first, when you walk in the maths department, you have your mocha thing there. They always show the solar corona because it's beautiful in multicolors, but I'll get to that. Okay, order out of chaos. Here we have the sunspots. Remember, I'm claiming that the sunspots are these things that emerge as a result of those shear layers in the interior that generate. If I start with a poloidal field and I have differential rotation, the differential rotation basically pulls it around and makes a torus out of it. That's called the omega effect. That's the easy part of a large-scale dynamo problem. The hard part of the large-scale dynamo problem is doing the opposite, turning this toroidal field into a poloidal component. But anyway, here are the sunspot counts, and you can see anybody in their head. I mean, you can do Fourier transforms in your head, right? So you can see there's an 11-year period here, right? And something else going on longer periods as well. And this has been changing over the years. But this is astonishing. The sun is beating like a heart on 11-year periods. Why is that? Play a game here. Who's that? Some of them are scientists, some of them are not. And I'll give you a clue. The width of the line is exactly their lifespan on the bottom panel. To quote Latanzio, this is some English bastard. It's William Shakespeare. Okay? Okay, the next one should be easier. No. Who's... Come on, guys, astrophysics. Galileo, there you go. Okay. Right. Newton lived during the Maunder minimum, where there were very few sunspots. Who are these two?
Well, bottom one looks like Ron Eakers with a beard. Is that Oscar Wilde?
Could have been, but it's actually James Clerk Maxwell. Yeah. The bottom one is Carrington, and Carrington appeared with that little star on the figure there. I think you'll agree that that star is in a place where sort of average, right, median behavior in the middle of the. There's nothing particularly special about where that star is on that plot, except it's near the top. Year is 1859. Who's that? Newton plus Maxwell equals Alfvén. Yeah. I always love this picture because I'd never seen anybody look so utterly pleased with himself.
Well, he did get the Nobel Prize for it.
Yeah, he did, yeah.
Half paper in Nature.
Yep. Here's more order out of chaos. The sunspots always appear in this fashion. So these are what they call synoptic plots. They always appear in like a butterfly diagram, which was discovered by Maunder, actually more by Maunder's wife than Maunder himself, I think. We have the original plot hanging in our observatory in HAO if you'd like to come up and see it sometime. But what I'm showing here is the sunspots always come up slightly tilted. So what does that mean? They always come up in pairs because div B equals 0. You can't have a unipolar sunspot pop up. But when they do pop up, they always pop up in a sense that if they're in the northern hemisphere, the first one is here, the other one's here. And they call the leader and a follower as the sun rotates. And the leader and follower always point to the equator. There are some that are anti like that, but those are very, very unusual. Again, a lot of order out of chaos. Here's the chaos. You can see it. See the convection there? Just below the surface, there's one hell of a lot of energy. 100% of the solar flux is being carried by convection. But in places where there's a magnetic field, that's changed. Okay, the next thing is another thing of order from chaos. So here we have the change from, this is the bit now where it should become a little bit clearer. So here's the butterfly diagram. Here are the butterfly wings. I'm not showing sunspots. What I'm showing is these are magnetic field measurements from the ground and from space over the last, up until about 5 years ago. And so they also include these funny things here. This is real. This is not noise or artificial. And what you can see is plus and minus every 11 years. If you look at the bottom axis, it's blue and then it's yellow, it's blue and then it's yellow. That's the reversal of the polar field. You can also see what appear to be waves of stuff coming off, going down from the sunspots into this region here. And current thinking is that owing to the eta del squared B term in the surface, in the magnetic field at the surface, that what's going on is that the tilt in the sunspots means that you've got more of one polarity than the other, and it's opposite to the existing one, and so it comes down and somehow magically cancels this out. That's a phenomenological description. It has physical basis in magnetohydrodynamic simulations at the surface, but it requires a diffusivity that's 8 to 10 orders of magnitude larger than the molecular one. Even for astronomers, that makes you feel a little uncomfortable. So you better take a look at what that's doing. Is that the right time there? Okay. So here's order from chaos. Here's a and in a way, I'm saying this is surprising. In a way, I'm saying it's not surprising. The thing that surprises me about it is that here we have such a remarkable beast as the sun that's capable of being so regular in its heartbeat, having so much structure in the presence of so much turbulence inside it. That's remarkable. But there is a breaking of symmetry here, and that is that the sun is rotating and it's differentially rotating. And that must be the reason why we get so much order out of chaos. If you could find a star that wasn't rotating at all, my guess is you might then look like that one in the non-fiction section. You might have to put that into the, you might have to put the fiction one into the non-fiction part of the library. But because of rotation, because of differential rotation, then I think this makes a little bit more sense. Okay. One of the big questions in solar physics is, I think, there is actually a belief that the surface magnetism itself is crucial to the operation of the dynamo. How to express this? I think that's a little anthropocentric. The fact that we can observe something at the surface and we watch it move from one place to another does not give me reason to believe that we're seeing cause rather than effect. But some people have taken it literally to mean that we are literally advecting field in these waves coming down from the sunspots towards the poles, and that is active in changing the magnetic structure of the pole. Furthermore, they add in the idea there's meridional circulation to drag that magnetic field down of opposite sign, which is the thing that then changes the toroidal field in the interior and completes the dynamo cycle. I personally am not willing to go that far and say, yes, that's the answer. I think there's a lot of things we need to figure out. One of the things we need to figure out is how to ask those questions and how to falsify things in this area. And that's a difficult thing to do. Okay.
Would this mean that the assumption that the surface is important, would this mean that we have convection in the core of the star and some radiated envelope on top, but we don't have cycles, don't have dynamo cycles in the core?
So the sun is an example of that star you're talking about, a redshift core and a convection zone.
Yeah, I want to reverse it and consider convection in the core and radiated envelope. So you don't have this so-called magnetosphere.
I don't know.
If magnetosphere is important, then you would argue that there are no cycles in the core.
Yeah.
But we now see very strong magnetic fields in the cores of giants.
Yes. Well, I'd like to talk some more about that. The sun is not atypical. These are looking at the sun as if it were a star, and the sun looks very similar to certain kinds of stars. I chose these from a sample from Balloonist et al. It's very straightforward. They're just the numbers in the top middle are the colors of the star, B minus V. So these are all dwarf G5 stars, pretty much. So I'm not looking at a heterogeneous group of stars here. These are solar-like. Some of them have cycles like the sun, some of them seem more random, some of them seem dead in some ways. About 30% of the stars seem to look like this, like the sun. So we're not looking at the sun because it's close and we can look in great detail and, you know, try to get to the understanding minuscule things like, we have wonderful words like bushes and mustaches and surges and all kinds of wonderful things that people botanize and talk about. No, that misses the issue, I think. I think we have very important problems. What this figure tells me is that the sun has chosen to be in a phase in its evolution or in its current state of rotation and differential rotation that it's producing a cycle, whereas it quite easily could have chosen any of these, but for some reason it's chosen to be in this state right now.
Do they have similar rotation rates?
Yeah. This best solar twin we have is called 18 SCO. In every regard it looks like the sun, except it has like an 8-year period for this kind of thing. Okay, I'm going to have to skip some things here. So in 1859, remember that little blue spot I put? Carrington was observing and with, you know, sitting in his back garden with his projected telescope and drew some pictures like this, which I thought I saw something on the beach that looked a bit like this the other day actually, but anyway, this is supposed to be a sunspot, and you see those horn white things there? Those are white light, what we now know as white light flares. Why is this interesting? Remember when I showed you that twisting of the field and it was getting into a hell of a mess? Something was, that's not compatible with what we see on the sun. The sun is much smoother than that in its coronal properties. And if you store that amount of energy, something's going to happen. And we believe that currently what's happening in the sun is that you store energy for a certain amount of time as it emerges out through the atmosphere into the coronal region, which is a big volume, low density. And then as you keep twisting and gradually changing things, there's just too much energy and some instability kicks in and the thing goes bang. That sends energy up and it sends energy down. If it goes down, you apparently see a white light flare. Okay? And okay, I'm going to step, that was very, very short time scales. Those things last minutes. Okay? So we've got a sun and that affects the Earth. That thing, that flare, a day or two later, they could send telegraph signals across the United States when they applied no voltage. That was just because of the induced electric field due to the changing currents in the ionosphere as a result of this perturbation. And people often ask the question now, what would happen if we had the 1859 Carrington flare tomorrow? Well, you know, I'm not a person into weather prediction or anything like this, but I think it's a fair question to ask, and I think that people on the space station would probably have to protect themselves rather well. It's a serious, serious business. Okay. On very long time scales, we can do something very interesting here. We can dig back in history by digging in the Antarctic and looking at tree rings. And we can look at cosmogenic isotopes. What's going on here is what I'm showing here is the neutron counting rate. The sunspot cycle is shown at the bottom, and I think you'll agree that there seems to be some kind of anti-correlation, 100% almost, in the nature of these things. And what's going on here is that as the sun is changing sign in its magnetic field, the cosmic rays, wherever they're coming from, are coming into the heliosphere, and the sun is modulating the rate at which they hit the Earth. So the muon showers and all the cosmogenic isotope changes that go on and leave their imprint in biological samples and in ice cores get imprinted. And this is just the last 50 years. So if we make a correlation between the sunspots and these things, then we can go back further and look at extrapolating what happens in the past.
Explain why it's neutron specifically on that plot.
The neutrons, there are such things as neutron monitors on the ground that are, I don't know to what extent you can easily measure charged particles on the ground. Cosmic rays, sure, I mean you get cosmic ray events coming through because you can see them on your CCDs sometimes. But since the 1950s there's been a record of measurements of neutrons for some reason. I don't know why. Does anybody know why? Are they easier to detect than protons? Do the protons make it to the ground? I don't know.
When you have a charged particle hitting the atmosphere, then you have the air showers. The neutrons is the most abundant secondary particle coming out of these air showers.
Okay.
And there are monitors all over.
Okay.
I think the neutrons can also easily induce reactions, and then you can measure the neutron which nuclei produce on these reactions, whereas protons don't react with easily.
Excellent. Thank you. I find it fascinating that when you say have a north-facing field in a solar atmosphere and a south-facing field, say we lived on Venus and couldn't see anything in the universe, this would tell us which direction the sun's pointing. There's a breaking symmetry. And that's because cosmic rays are primarily positively charged. And if there was a balance between positive and negatively charged, there would not be this asymmetry between the pointed looking ones and the flat top ones in that graph. It took me a year to figure that one out, why that was the case. Okay, so what's going on? Here's the mechanisms. Tree rings, ice cores, spallation, galactic cosmic radiation. And what do we see? Well, here's a Fourier transform, and there's the periods shown. So Fourier transforms are funny things, but so this is a sort of quasi-periodic, not really periodic, but it shows you've got a lot of power at very low frequencies. The sun also is doing things on periods. So the very rightmost one is a 50-year period, I think. And so you've got records, that show that the sun's varying on timescales. You can't go back beyond about 10,000 years because the climate changed so rapidly. So we have that period since the last ice age that it kind of messes up. There's a zeroth order effect that's bigger than this effect that could cause people problems if you try to go further back than that. But what I'm trying to point out is that the sun is variable on a lot of different time scales, much faster than the Kelvin-Helmholtz, etc. So if we're going to regenerate the magnetic field as a dynamo, how are we going to do it? This is essentially in the magnetohydrodynamics equation we're dealing with. We can either solve that with the equations of motion in a dynamical sense. The problem there is that you try and fit the sun into a box, you can't do it because you've got so many scale heights, you've got all this structure involved, you've got eta being so small that you're going to end up with eta being 8 order of magnitude larger than reality simply because of the numerical scheme if you put in a discretization, if you're not clever about it. So one of the things people do is they fix a U, don't solve an equation of motion, and they play with these equations here, and they play with values of eta as a function of depth and what have you, and they look at whether they can produce a dynamo or not, and those are called kinematic dynamos. So if we look at differential rotation, you can actually look at what's needed to make this kind of thing work. And the point of this graph is just to show you that to make something like this work with a 1 over t being 1 over 11 years, you've got to have a set of conditions such that if I were to literally take this equation and allow it to be partially dynamic and not fully kinematic, I would separate scales. I would use a large scale U and I put a small scale U. Then I could use a small scale U and a small scale L in here, and I would get an eddy diffusivity. And I would use a separation of scales and try to solve for the large scale magnetic field and a large scale U. And then if I did that, I'd end up with having to get a value of the diffusivity, which is around 10 to the 11, 10 to the 12. That just says that, you know, given the internal differential rotation given by a vector field u, in order to make this thing come and go on 11-year timescales, that's the number I'm going to need on the right-hand side. It's as simple as that, really. So what we've concluded is that then this system must be turbulent, not kinetic in nature, which is perhaps not surprising, but there are problems with this. So here's the mean field theory, where you split it up into larger small scale components, and you end up with a turbulent diffusivity, and you end up with a which is eta plus beta, but you end up with an alpha term here. So remember I said the twisting of the magnetic field is the twisting up horizontally is the omega part of the dynamo. This is the alpha part, and so you end up with an alpha omega dynamo. And what this does is this is efficiently converting toroidal field back into poloidal field, and it works through the inspired by Parker, it works through basically the emergence of bubbling up material in the presence of a Coriolis force of a particular sign, and that gives helicity, which is what you need to make this thing. And this is a helicity generating machine, a curl of alpha B0. Okay, so again, it's a prescription for getting order from chaos. They can be very successful. The problem here is that when you have you can construct dynamos that look real from different prescriptions. That's a real problem in science. How are we going to tell the difference between the two? And they're not perfect. They're not meant to be. They're meant to explain the large-scale evolution of the field. I don't think that's the big problem, though. I think there are serious problems with the concept of a diffusivity. And this is highlighted by a paper by Parker in 2008. Basically what these Bolt models do is they allow you to take a fluid element and move it a distance L with a velocity V, and then you replace your del squared B term in the equation of the induction equation with, instead of the molecular mean free path times the thermal speed, you replace it by the bodily moval of a piece of fluid and a mixing length. Okay? That's fine for a scalar field like smoke. I mean, if I have bad breath and I walk in a room, you know, within a second or two, if my breath is bad enough, the people at the bad can tell, oh my God, that guy's got bad breath. Now that's not molecular diffusion. That's convective sort of diffusion going on with that. The thing is here we've got a vector field, and that's not the only problem. The real problem is you've got a J cross B force. So when I'm pulling on this fluid element, I'm also pulling on the magnetic field. And so I'm not allowed simply to just plug in a eddy diffusivity, mean free path, because the Lorentz force, and the problem that Parker points out here is that actually at least half the time the magnetic field is going to stop the diffusion happening before it gets there, because the Lorentz force is going to dominate. This comes back to a central theme I wanted to talk about. Remember the birds at the beginning had this whole collective behavior that was very big. This is the same kind of thing. Here we've got a tiny, tiny thing happening on molecular, almost molecular scales, with small Lorentz forces not allowing the diffusion to happen, having an effect on something very, very, very big. So it's this coupling between the large scales and the small scales and the nonlinearities which the sun has in common with things like flocks of birds, the patterns you see in flocks of birds, the patterns you see in the response of an immune system to a protagonist. One part of the immune system doesn't know anything else about any other part, but together the sum is incredible. We wouldn't ever, none of us be here if it weren't for that effect. So I'm kind of asking the question, and I don't know if anybody's familiar with complexity theory in any formal sense, but whether we should look at the sun in this complex theoretical system, as a complex system. We solve the nonlinearities using partial differential equations because that's how we know what to do. I wonder if there's some benefit to looking at this thing from some other point of view in terms of cellular automata or something. I don't know. Something, there may be a different way of looking at this problem. Okay. I'm going to step right forward here, and there are several problems with the dynamo models. I want to finish up by drawing your attention to something which I like. So I ran downstairs and took this picture a few minutes ago, and it's your, I don't have to explain it, but what I will do is explain the following. There's something really, really odd about this image, and all others like it. It's not Monash's fault. This is a perfectly good, fine image. But you may not realize, well, in my mind at least, there's something very peculiar about this, and I'll tell you what that is. This Fred Hoyle looking particularly cheerful, yes. So this is just a movie of going from the photosphere into the corona. And one of the grand challenges identified since Ed Lane was 1943. What is heating the corona? That's the grand challenge. I'm going to point out another one. Why is there so much order in the corona? People say, oh, look how much fine structure there is in the corona and the transition region and everything. Oh, it's all a complete mess. No, I disagree completely. I think there is so much order in the corona, it's embarrassing. Because we know that the dissipation is going on tiny, tiny scales. How do you communicate the dissipation over many megameters to let this part of the corona, which is essentially energetically there's no transport of energy across fields, how's it going to know how to be at more or less the same temperature as this part? Let's get to that. This basically says what I was saying here. There is an irony and poetic consequence of ideal MHD, and it's called the spontaneous current sheets and magnetic fields. The second book you've seen, the first one is very challenging mathematical book for me to read personally, but there are people with much better skills than me that would have no problem with that, I think. What's going on? In the corona, there's nothing left to fight with the magnetic field. Pressure gradients aren't very strong, anything like this. The magnetic field is, if there's an electric current in the surface, and say it's a dipole, it drops off as 1 over r cubed, elementary magnetostatics. The atmosphere of the sun, though, is exponentially stratified. So there's almost nothing in the corona. There's 10 orders of magnitude less particles per cubic centimeter in the corona than there is in the deep photosphere. 10. So that means that if the sunspot can affect the photosphere, you know how much it's going to affect the corona above it. I mean, it's already stronger than the photosphere, a very deep sunspot. 10 orders of magnitude less particles. So that means that in the equation of motion, J cross B is 0. It's saying that whatever happens, if I have a slight departure from J cross B equals 0, J cross B will exert such an enormous force that within a very short time scale, namely an alphane speed, it'll relax to a state where it is 0. Okay? If that's the case, J cross B is 0. J is curl of B. That means I can write identically curl B as alpha times B. I can operate on that with a curl operator and get complex characteristics, but then I can operate with a divergence operator. Alpha is a real constant along field lines. It actually is the ratio of the current to the magnetic field. That means that this field line doesn't know anything about this field line. They can be infinitely close together. That alpha can have any value from this point to that point, depending on what the photosphere decides it's going to be. That means that I can twist it this way, I can twist it that way. But whatever I do, these field lines have real characteristics. They don't know about each other in this direction. And so I can get any level of complexity between these two field lines in the neighborhood of each other, anywhere above this surface, providing this equation is valid. There is no requirement for the measure of circulation or torque to be continuous from one field line to the next. And there are various proofs of this that have been come up. The consequence of this is that Parker claims that with an untidy field like at the physical surface, you get magnetic stresses steepening without, acting alone cause the magnetic field gradients to steepen without limit. This is in the ideal case. When you see things steepening without limit, then you have to go back to your hydrodynamics and say, well, I wonder if the hydrodynamics is breaking down. Of course, then you're going to get into the realm of a little bit of plasma physics and kinetics at the very least. Okay, let's finish up. Here's an example, a numerical simulation of 2.5D, if you like, this is Rapazzo et al.'s work using reduced hydrodynamics. Yeah, I won't go into the details. Formation of current sheets in numerical simulations. This is very, very difficult to do in numerical simulations because you automatically have diffusion if you're solving a partial differential equation across these things, and so you tend to smooth these things out. So you have to be careful how you do this, but nevertheless, with modern computers, you can do this in some level or other. So here's a real tragedy here. Ideal MHD plus untidy fields leads to tangential discontinuities. Genuine tangential discontinuities cannot form in the presence of a small but finite resistivity. Therefore, in trying to become singular, the Maxwell stresses make steeper gradients until ideal MHD causes its own demise, which is why I put my favorite actor doing Macbeth there. That is one of the grimmest Macbeths I've ever seen in that film. So what's happening is ideal MHD applied to a J cross B, a force-free field limit, causes its own demise, and it automatically leads to dissipation of energy. Then you end up with a conundrum. Well, the first thing is, the thing you've gained about it is that you've gained a theory of heating and dissipation. This is the puzzle. This is all blue. This is all, I'm colorblind, some other color. There's some white things in here, which are mixtures of colors. If there's no way to transfer information from one field line to the next about the temperature, and remember the actual ion gyroradio around these things are meters. This is like 1 megameter here, a million of them, so it's negligible. Any kinetic effects are tiny. How does this all know, everywhere, to be roughly at the same temperature? And how does the active region know to be roughly at another slightly different temperature? In other words, why is this not all just grainy black and white with structures in it? Why? Because each temperature there is represented by a different color. Why is it all over the place? I can think of one reason, and that is electron field conduction. But that again is like the real characteristics. That only applies along the field lines. There's some way in which the sun knows how to heat the corona, not only along one field line, but similarly along many, many others. We even have things called coronal holes, which have huge things, which all know about being at the same temperature. So where is this coming from? I don't know. So I'm going to finish by saying what profitable lines of inquiry are, and I want to draw your attention to a thing called DKIST at the bottom right there, which is trying to get down to the limit at which magnetic field diffuses on the surface of the sun, so that we can finally understand the relationship between the large-scale dynamo and the diffusive processes right at the base of the atmosphere. I would say that, in fact, we have an embarrassment of models of various kinds. I mean, if somebody published a paper saying we got a new model for coronal heating, that's fine, except we've already got 10 to the 12 of them or something. And it's not quite that bad. But it has prompted one of my colleagues, Robert Rutten, to say, well, we've got so many mechanisms, why is the corona only at 1 million degrees? Why isn't it at 20 million or 1,000 million? Okay, that's a facetious comment, but the point is that refutation should be in the game. We should be able to try and refute certain models of coronal heating. And that's not a popular way of doing research. You try and get your paper published if you're refuting people's models. But that's what the game is, I think. Finally, I believe the right stuff is to measure the magnetic fields, obviously. And we haven't been doing that too well. And so I'm just going to finish by letting you think a little bit about that. We're observing from a distance. And if we were to look at that thing and not know they were birds, what would we conclude? If we took a snapshot then, what would we conclude? Thank you.